A rotating system can be described by storing every full orientation, but a smarter model stores small changes between orientations and rebuilds the full motion when needed. This lesson connects rotation, compression, and probability by turning a gear-like chain of Quaternion rotations into a mathematical update rule. The goal is to make the proposed pump idea precise enough to see what the equations can represent and what conditions would be needed for stable motion. The moving parts in this model are orientations, so the first mathematical object is a unit quaternion, which is a 4-number rotation code whose length is 1. A unit quaternion can represent a 3-dimensional rotation without the axis locking problem that can happen with pitch, yaw, and roll angles. If one frame has orientation q sub k and the next frame has orientation q sub k plus 1, then the rotational change between them is the delta Quaternion delta q sub k equals q sub k plus 1 times the inverse of q sub k. That equation means the delta stores only the twist needed to move from one frame to the next, rather than storing the whole orientation again. To rebuild the chain, the next orientation is q sub k plus 1 equals delta q sub k times q sub k, and repeating this multiplication walks through the rotation history. For the 12-point gear with 720 frames, the full chain can be written as q sub 0, q sub 1, all the way to q sub 719, with 720 delta steps arranged around the cycle. For the middle 10-point gear running inverse, its 72-frame chain can use deltas r sub k equal to the inverse direction of the matching course rotation, so its update can be written as p sub k plus 1 equals r sub k times p sub k. For the lowest 8-point gear with 10 frames, its chain is an even coarser level, so each stored step summarizes a larger part of the motion. This is delta encoding, because the large chain keeps detailed changes, while the smaller chains keep larger summarized changes that can help reconstruct or check the motion. The scaling in the frame counts is important because 720, 72, and 10 create layers with different time resolutions, even though they do not divide into one another perfectly at every gear point. A clean way to connect the layers is to define a projection rule from the fine chain to a coarse chain, where a coarse delta equals the product of several nearby fine deltas. For example, a coarse step can be built by multiplying delta q sub a, then delta q sub a plus 1, and continuing through the fine steps that belong to the same coarse interval. Because Quaternion multiplication is order sensitive, the deltas must be multiplied in the same time order as the original motion. The word inverse in the middle gear can be modeled by using inverse quaternions, which undo rotations because a unit quaternion times its inverse gives the identity rotation. If a fine layer rotates forward by a delta, an inverse layer can rotate backward by the inverse of that delta or by the inverse of a grouped product of deltas. The Markov part describes how the system moves from one state to the next using only the current state, not the entire past history. A Markov chain can be written with states for gear positions or orientation bins and transition probabilities that say how likely the next state is. For a torsional pump, a directed current from state I to state j can be described as pi sub I times k sub ij minus pi sub j times k sub ji, where pi is the chance of being in a state and k is the transition rate. A positive total directed current means the transitions favor one cyclic direction, so the system behaves more like a pump than like random back-and-forth motion. To combine the Markov idea with Quaternion deltas, each transition can carry a rotation label, so moving from one state to the next also multiplies the current orientation by a delta Quaternion. The complete update can be written in words as new state equals a Markov transition from the old state, and new orientation equals the transition delta times the old orientation. Algorithmic memory offloading means the system does not store every full reconstructed orientation on every layer. Instead, it stores the starting orientation, the delta chains, and the rules for grouping and inversion. When a detailed frame is needed, the system multiplies the needed sequence of deltas from the nearest stored reference, which trades extra computation for less stored memory. Perfect equilibrium is not automatic, so the model needs closure conditions that make each cyclic product return to the identity rotation after one full loop. For the 720-frame chain, That closure condition says the product of all 720 delta quaternions around the gear should equal the identity quaternion. The same kind of closure condition is needed for the 72-frame inverse chain and the 10-frame coarse chain if they are meant to cycle without drift. Numerical systems also need renormalization, which means each quaternion is adjusted back to length 1 after calculations, so tiny rounding errors do not slowly turn rotations into distortions. A precise mathematical expression for the proposed pump is therefore a layered Markov chain, whose transitions carry unit Quaternion deltas, whose coarse layers are products or inverses of fine layer deltas, and whose cycles satisfy identity product closure. In that form, the idea becomes a testable model. Data can flow between detailed and compressed rotation layers, but stability depends on ordered multiplication, consistent grouping, inverse updates, and periodic correction of rounding error.